can write down the title, so that's just writing the title. Exactly, that's why. It's a long title, so. Is that the title I gave? Yeah? Okay, great. Roughly?
I thought it was just surfaces.
Ah, surfaces, yeah, sorry, yeah. I don't pretend to go beyond dimension 2. Yeah. Yes?
Good morning. So it's a pleasure to introduce Marcello Bernardara to speak about semi-orthogonal decompositions and rational surfaces.
Okay, thank you very much for inviting me here to give this talk. And I just take the possibility to advertise a summer school, very nice summer school. On derived categories, and will be held in Nantes. Very nice town in June. Very nice period in the year to be in Nantes studying derived categories. So there is funding for young postdocs and students. If you want to come, there will be 4 courses, and each course will have exercise classes, so it will be really an interesting school for people who want to have a bit more on derived categories. Okay, so the poster disappeared, so and I'm really angry about that. I'm really upset. So there was a very nice poster here, white with the yellow tensor product, and someone took it away. So I wanted to hang the poster on the blackboard, but okay. So advertising is over, and let me start with my talk. It's a joint work with in progress with Auel, and I will start with an example to somehow give the idea of what kind of things should go on to understand the birational geometry of geometrically rational surfaces. So we take K be any field, and see, you can consider over K X Browser variety. And then to this variety, you can means that this variety, when you go to the algebraic closure, the base change of this variety is just a projective space. Okay. So it's isomorphic to the projective space over the algebraic closure. So for example, it's a conic. The Browser curve is a conic, and so on. And to such a variety, you can attach, you can associate naturally an element in the Brauer group. So central simple algebra over the feed K, and there is the Emitzer conjecture. So this algebra determines the isomorphism class. Of X. So it's if you can think of this algebra as giving you the abstraction to construct the hyperplane section. Okay? So this is not really a projective space. But when you go to the algebraic closure, here's the projective space. So you have kind of line bundle, which is the hyperplane section, and then the abstraction to give the same, to glue the état local sheaf, which is the hyperplane section, is given by this element of the Brauer group. And Emitzer conjecture says about the birational class of it's about the birational class of such varieties, and says that XX prime and the Brauer-Severi varieties are birational, so K birational, so there exists a birational map over over k as k varieties, if and only if A, the group generated by the element A and the group generated by the element A prime are the same inside the Brouwer group of K. Okay, so you can check that if you have such a variety, this element is finite order in the Brouwer group. And so these are like cyclic groups generated by the class. And so this conjecture is known for surfaces, for example. So if the dimension of X is 2, it means that the order of A is 3. Somehow if dim X is 2, then the group generated by A is just as a set. I mean, you have the identity, so the trivial class. You have A and you have A minus 1, depending you want to use additive or multiplicative notation. Okay, so this is, and the fact is that actually the identity you don't really care. So the fact is the birational class of the Brouwer-Severi surface is determined by this pair of algebras. Okay, these two algebras. So the obstruction to descend the hyperplane to the field K, and the obstruction to descend O minus 1, if you want, to the field K. Okay, so this is a very classical result of Roquette. And yes.
Is there an easy implication that left to right is easy, or they are both?
Left to right is easy. Yeah, left to right is known for any dimension, and right to left is very difficult if you just suppose that you have two classes generating the same subgroup in the Brouwer group. Then you have the associated Brouwer-Severi varieties. How can you give the birational map? This is a big mystery. So if they are birational, it's Amitzer's theorem is this direction. So from birationality to the equality of the groups. And he conjectures that this is an if and only if. There are also other cases where it's known, so like sparse cases when you suppose that, for example, the order of A is, okay, is still a very difficult thing to, given just abstractly two Brouwer-Severi varieties, to determine if the birational map exists. Okay, so this is known for surfaces, and somehow the idea is that this pair of algebra, this pair of central simple algebra over K, determines determines the birational class, the birational equivalence class of the surface. Okay, so when I say that A determines the class of X, it means that if I take A minus 1, it's not the same. They're not isomorphic. Okay, they are birational but not isomorphic. So there exist non-isomorphic birational Brouwer-Severi surfaces. Okay, so where do derived categories and semi-orthogonal decomposition come into play here is for the following result. So there exists a semi-orthogonal decomposition. I use SOD for semi-orthogonal decomposition. So the bounded derived category of coherent sheaves on X. And I will just write it like this. You have the derived category of the field. Then you have the derived category of A algebras over K. And then you have the derived category of the nth power of the algebra A over K. And you have to think of this semi-orthogonal decomposition somehow as base changing, so descending. So you can base change this semi-orthogonal decomposition, and you get that the known Bailinson decomposition for the bounded derived category of projective space. So this is just the projective space over the algebraic closure, and you have O of 1, O of n. Okay, so these vector bundles, these line bundles are defined over the algebraic closure. And what happens here, how do you descend this semi-orthogonal decomposition to the base field K? You have you can see that there is you cannot define O1. The definition of O1 is obstructed by the existence of O1 on the Brouwer-Severi variety is obstructed by this algebra. And what you can introduce, this is really a classical result by Quillen and other people like this, you can produce a rank 3 vector bundle. Vector bundle over X, such that when you base change, so I will use this notation to mean tensor spec k bar. This is just 3 times the hyperplane section. Okay, so somehow you have an étale cover of X where this is defined, and to glue properly if you want to glue properly your hyperplane section, you have to take a higher rank vector bundle, and the rank of the vector bundle you consider here is related to the order of the algebra that we have here. So you have the algebra over the tree. Yeah. So for surfaces. Ah, sorry. Yeah. Okay. So this is rank n+1 on X, and sorry. Okay, I was already into the surfaces. Okay, but this is general for any Brouwer-Severi variety.
It is indecomposable, this bundle?
It depends. It depends. It is I mean, for surfaces, it is indecomposable because you know that the order is 3. But if the order is not prime, you can have like splitting of this because, I mean, it's delicate. But you have to think as this V as a tilting bundle. So V is a tilting bundle for this piece of the semi-orthogonal decomposition. Okay, for say D1, for the category D1. So you can check easily. This is a classical result of, that's the way you associate, exactly the way you associate the algebra A to the Brouwer-Severi variety. That's A is the endomorphism algebra of V. Okay, so that's exactly, if you want the definition of the algebra associated to the Brouwer-Severi variety. Okay, and you can see somehow that since the algebra A has order n, that in this semi-orthogonal decomposition, it appears that you have all the components, each component gives you exactly all the elements in this group. Okay, so somehow the semi-orthogonal decomposition carry over the information of the Amit, or so of the group generated by the algebra, the subgroup of the Brouwer group generated by the algebra A. And what's the important point here is that Morita equivalence for central simple algebras over a field is just isomorphism. Brouwer equivalence and Morita equivalence are the same. So in Brouwer K, of K, any field, even any Noetherian ring, I guess. Sorry, I will write this on the other table. So if you take the Brouwer group K, Brouwer equivalence is Morita equivalence. Okay, so exactly, if you think about this semi-orthogonal decomposition, it gives you exactly the same data because it's defined up to Morita equivalence, but Morita equivalence is Brouwer equivalence, so you get the semi-orthogonal composition encodes the same data, encodes exactly the data about the subgroup of the Brouwer group generated by the algebra A. Okay, let us go back to surfaces. So if X, let me use the letter S for surface. So S is a Brouwer-Severi surface. What's the semi-orthogonal decomposition in this case? So it's dBk, dBka. So when I note like this, it means the K linear category of A algebras over K. Okay, so of modules over the A algebra, of modules over the K algebra A. Okay, and then you should have A square, which is A minus 1, since this has order, since the algebra is order 3, and. Yeah, A tensor, the third tensor power of A is the direct sum of K, so it's a matrix diagonal algebra.
So A to the power is the...
A to the power n plus 1.
Is the tensor power of A with itself several times over K, is that right?
So the n plus 1 tensor power over K with its, of A with itself, so here, if you want, okay, let's is not K, is a matrix algebra, a diagonal matrix algebra, but it's Brouwer equivalent to 0. So it's 0 in Brouwer K. So it's 1, sorry, I use a multiplicative. Okay, because it's, yeah, A up. Yeah, I mean, there is lots of different terminology. This is my choice. You can write it as A up, because you can, if you want, you can think this as matrix algebra. So endomorphism, exactly, you can define these algebras as endomorphism of vector bundles over the field K.
What is this derived category of KA? Is everything split as a sum of?
No, this is indecomposable. This is indecomposable, because K is a field. You can show this.
I mean, like the first one is just graded K vectors, basically.
Yes, and
The second one is as simple as that.
yeah, these are A is a simple algebra, so it's exceptional if you want in some sense, and yeah, you have like it's a bit more delicate, but you can think this as this category is not a category of twisted sheaves over S. It's a category is a way to plug twisted sheaves over K, A algebras into untwisted sheaves over S. And the idea is that this vector bundle V, that is the tilting bundle for this category, is exactly the way you trivialize O1. Okay? So if you take here the algebra A, which is the generator of this category, so you have a Fourier-Mukai functor from this A algebra, category of A algebras, and the image of the generator, which is the algebra A, is the vector bundle V. And you can show actually that everything which is twisted by something of order 3, as here, has rank at least 3. So vector bundles of rank which are multiple of 3, because it's some way you have to glue it. You have to pass it to an étale cover and then take direct sums and then descend this direct sum. Okay, so this is the point. What happens, just a remark on this semi-orthogonal decomposition, this is just a choice. We could have chosen another semi-orthogonal decomposition just by abstractly mutating these two categories. So the order I give in the semi-orthogonal decomposition is not very important, because you can, so somehow the semi-orthogonal decomposition really contains the information on the generation of on the subgroup generated by the algebra A. And in principle, this is just a choice. Okay, if you want to descend, for example, if you put O minus 1 here instead of O2 here, when you want to descend your exceptional sequence on the projective plane, then you will get the mutation of this. Okay, and you will get A minus 1 here. Okay, so this is the idea. So somehow we can see inside the derived category of Brouwer-Severi variety a pair of algebras arising somehow as in a natural way, which encodes the birational properties of X. And the other remark is that S is rational. I mean, S rational, when I will say rational, means k-rational, already birational to the projective space on the base field. This is equivalent to S having a point, and this is equivalent to A being 0 in the Brouwer group. 1, sorry. So if you want, or this is equivalent also to the vector bundle V to split. Okay, so this is true for any Brouwer-Severi variety, but you can, I want to stick to surfaces in this case. Okay. So somehow you see that also the semi-orthogonal decomposition has some non-commutative components that become commutative as soon as the variety is rational. Okay, so somehow you can say that I will give the proper definition here, but keep in mind I want to say that geometrically rational surface is rational if and only if it's commutative in some sense or zero-dimensional in some sense. Okay, I will tell you more in short. Okay, just a little remark about what I said on Brouwer equivalence and Morita equivalence. Let me state it as a lemma in a better way. in a more clear way, because it's true for in more generality as the follows. If I have k, big K over little k in étale algebra, and k prime over k another étale algebra. So if you're not familiar with étale algebras, you can think of them just as product of field extensions, of finite field extensions of k, and A in the Brouwer group of this étale algebra, and A prime in the Brouwer group of this other étale algebra. So once again, if k is the product of finite field extension of little k, then this Brouwer group is just the direct sum of the Brouwer groups of the field. So this is the data of a finite number of field extension of k, and for each of these field extension, an element in the Brouwer group. And we can show that you can go on with this slogan, Brouwer equivalence is Moride equivalence, that I have hidden behind the table by showing that dbk prime A prime is equivalent to dbk A if and only if k prime is isomorphic to k, say via an isomorphism phi, and phi star of A is Brouwer equivalent to A prime. So this slogan, Brouwer equivalence equal Moride equivalence, is true not only in the Brouwer group of k, but in the Brouwer group of any étale algebra over k, which will be useful later because we will have to deal with this kind of more general thing than just descending line bundles. Okay. It's Brouwer k prime, yeah, thank you. Okay, so somehow if you take another Brouwer-Severi surface, dbs prime, so S prime Brouwer-Severi surface, and dbs prime, you write it as dbk. I write something that I already said, dbk A prime, dbk A prime minus 1. Then these two algebras are Moride equivalents to these two, if and only if they are Brouwer equivalent. So somehow this, I already said this. So I can write down the slogan if you want. If you have a k birational map here, if and only if this is Amitzer conjecture, say the set, if you think to the pair A minus 1, if you want, as a group with the law given by the law induced by the Brouwer group, and is equal to the set A prime minus 1. You can think of sets or either of sets or subgroups of the Brouwer group, if and only if these are Moride equivalents. Okay, so if and only if. Yes. Yeah. I mean, sorry, it's true for surfaces. I think it was proved by Roquette in the 50s or something like this. And so this is they are Brouwer equivalent, and if you want, I can say that I can write it like this. There are Moride equivalent. There is a Moride equivalent pair of algebras on K. Okay, so I don't know if A is A prime or A prime minus 1. I cannot control this, but I know that there is a pair of algebras and they are in bijection to each other, and they are Moride equivalents in pairs. Okay. So the idea is that this non-zero dimensional part of the non-commutative or non-zero dimensional part of the derived category controls the birational behavior of our surface. Okay. So let me just now finish this example. Once finished this example, I just point out two important questions that were raised. The first question is due to Bondal and Orlov in their ICM address in 2002. They say that semi-orthogonal decomposition should be should give away to analyze rationality problem. It's not a question, it's a guess, as I write it, to analyze rationality questions. That's the first question that has been worked out by, in the complex case, since that time by Kuznetsov and other people with satisfactory answers for threefolds and for some that, for example, everybody knows the conjecture on fourfolds, and the cubic fourfolds is rational if some subcategory arising in some semi-orthogonal decomposition is geometric in some sense. And there will be lectures on this in the summer school. And the second question is a question which was pointed out to me by Hélène Henault when I was a postdoc in Essen. Does the derived category of, say, any variety, but in this case a surface, contain information on the existence of rational points? So this is based on the idea that if you remember the way that is proven that for ample or anti-ample canonical bundle, you can reconstruct the isomorphism class of the variety by the derived category. From the derived category, you use point-like objects. So somehow you have a homological way to identify points, actual close points on the variety. And the idea is that can we go a bit further, have something more fine, something finer about this question. And I warn you because we have been discussing of this at a meeting in last year for the case of elliptic curves is already a very hard question. Okay, so it's interesting, but it's hard. So I prefer to take a look into geometrically rational surfaces, which should be somehow easier to handle from a geometrical point of view. I just tell you by words that it should be also some motivic reason to think that the derived category should contain information on the existence of a point, because if you have a point, it gives you a splitting for the Chow motive. So it gives you can split off H0, and you can split off a Lefschetz motive in codimension 2, for example, for surfaces. And this gives you some splitting of the Chow motives and with integer coefficients. And somehow the derived category should contain the same information from a non-commutative point of view. So semi-orthogonal decomposition gives you the decomposition of the non-commutative motive, and somehow these things should be related to the existence of sections given by points. So the way splitting off a Lefschetz in the Chow motive should somehow have a non-commutative counterpart, but it's still quite hard to understand. I don't know. For geometrically rational surfaces, true. No, so the question is already for elliptic curves it's very hard. Yeah. That's the place usually you want to start with, right? Elliptic curves. You have non-isomorphic elliptic. You can wonder if over K, over a field which is not algebraically closed, what happens to? So genus 0 curves and elliptic. Genus 1, sorry, curve, not really elliptic because you don't have a point. You have and it's a mess. But would be very interested in knowing some result of this kind.
Fields do you have in mind?
Any field. Any field is fine.
And what interesting choices do you have? I mean, coming from rational, do you have points on varieties?
You have this. So, yeah, or you can have number fields, for example, or all of them. Yeah. So these results, I mean, what is interesting from the derived categorical point of view is that this question of Bondal-Orlov was studied a lot for complex varieties because maybe it's easier to handle and so on. But the technical material you develop with the semi-orthogonal decomposition and the exceptional object and so on is just independent on the field. So you can really try to go on over any field and try to attach some invariant to the variety. And that's yes, he's doing something on this. We discussed of this last year in AM. But did you write the paper? Ah. Okay. So something for elliptic curves is known, but I wasn't aware. Sorry. Antio, Ben Antio. I write it. Okay. So let me just give how to answer Bondal-Orlov question. There was this idea of Kuznetsov of defining what should be some kind of Griffiths component of the derived category, but somehow is tricky because it should be the component in the some semi-orthogonal decomposition that is not of codimension 2 in some sense. But we should need some strong property on semi-orthogonal decomposition of on the derived category, which are not true in general. So let me give a definition by which we can try to bypass this point. So I take T to be a k-linear triangulated category. And I say that T is representable in dimension D, say, if there exists X, a K variety of dimension D, smooth and projective, and a fully faithful functor of T inside the derived category of X, admitting an adjoint. Okay, you need the adjoint because if T is not geometrical, you don't know if this gives rise always to a semi-orthogonal decomposition. So the adjoint means that if and only if you have a semi-orthogonal decomposition of X by T and is right orthogonal. Okay, so it's somehow a category is representable if you can plug it into some geometric context. Okay, and I say that a variety X is categorically representable. You will hear more about this in Michele's talk tomorrow or on Thursday. If in dimension D, sorry, if there exists a semi-orthogonal decomposition by categories T1 up to T, say, S, with the Ti representable in dimension at most D. Okay. So if you check the semi-orthogonal decomposition over there, the first piece, dBk, is representable in dimension 0 because it's the right category of a point. But A prime and A prime minus 1 are not representable in dimension 0 because there is no zero-dimensional variety that has such subcategories. Indeed, you can prove. It's not very difficult to prove using some result of Toen. Categorically representable, sorry. Yeah, okay, yeah. I mean, it's, yeah, yeah, but I don't want to, I actually want a commutative stuff. I wanted to live inside some, I mean, if you think non-commutatively, this Ka prime is representable in dimension 0 as a non-commutative variety. See? So I really want to have something commutative. And indeed, the proposition, so the lemma, if you want, is we have proved with Asher is an easy consequence of some work of Toen on derived algebra, on derived Azumaya algebra, is that a category T is representable in dimension 0 if and only if there exists an étale algebra of a K and an equivalence between T and dB of K. Okay, so I should write little kk, so it's the K-linear category of big K algebras over small k. So somehow this is the spectrum of a finite number of points of finite length over the K, over K. So a spec of K, since K is a product of finite field extension, is just a finite collection of finite length points over the base field K. So it's somehow zero-dimensional as a scheme. So the scheme spec K is zero-dimensional. Okay. And so here comes the theorem, the main theorem we are proving with Asher. Is the following. So no, dBk is geometrical, so it's dB of spec K. It's a zero-dimensional scheme. It's a zero-dimensional K scheme. No. Yeah, I should write it like this, right? So it's the isomorphism, the equivalence is K-linear. Okay, you should think of this as a variety which spec K is just spec. It's just spec of some product of field extension, of finite field extension. And so it's just a finite set of points. It's a smooth projective variety. It's not connected, but who cares? Okay, you can see this as just a union of points, and you can take the of finite length over the base field, and you take the spectrum of each. No. But anyway, you can. Yeah, it's not connected. No. Otherwise, what you do is writing this is easily decomposed as the product of dB L1, dB Ln. But I don't want to write down this every time. So you can say that T is split as a semi-orthogonal decomposition by derived categories of field extensions of little k, if you prefer. So the theorem is the following. I will tell you later some details on geometrically rational surfaces. So a surface is geometrically rational, but when you go to some field extension, it becomes birational to P2. Okay, and I say that the Pezzo surface S over K is k-rational. Sorry, if and only if it is categorically representable in dimension 0. Means that there exists a semi-orthogonal decomposition by field extensions of the little k. Okay, and the second thing is if S is minimal. So minimal is the same definition as in the complex case you are used with. There is no birational map to something which is not isomorphic to S. Then this happens if and only if. Then say this happens if and only if Sk is non-empty, and happens if and only if the degree of S is at most 5. Okay. Most of these results are well-known results for the classification of surfaces. So we just add the categorical interpretation of these things. Okay. And moreover, there exists a pair of algebras B0, B1, which are Moride equivalent to Azumaya algebras. Say I would write it like this: K1 A1, K2, A2. So A1, AI is in the Brouwer group of Ki, and Ki is etal over K. Okay, still in the minimal case. Okay, and in the that determine this pair of algebra determines the birational class, determining the birational class of S. Meaning that if S is birational to S prime, then there is this pair of algebra in the semi-orthogonal decomposition of S prime, as in the case of the Brouwer-Severi surface. Okay, if and only if the pair K1, A1, K2, A2 is Moride equivalent to the pair K1 prime, A1 prime, K2 prime, A2 prime. Okay, so you can think of this as extending what I told you about the Brouwer-Severi surface case when K1 and K2 are just the same, the base field, and A1 and A2 are A and A minus 1.
Why do you write A2 and not A1 minus 1?
Because in other cases, like for quadrics, it's not AI minus 1. It's just a pair of algebra which have nothing to do with each other. Indeed, the Brouwer-Severi case is very special, and a consequence of this is that the minimal del Pezzo, as a consequence, minimal del Pezzo of degree non-rational, sorry, I should add non-rational because otherwise what I say is stupid, non-rational minimal del Pezzo of degree D, which is in between 8 and 5, are rigid, are semi-rigid. So any birational equivalence can be composed with another birational equivalence, giving an isomorphism. So it doesn't mean that, so rigid, birational rigid means that the birational equivalences are the isomorphisms. Semi-rigid means that you maybe have some birational map, but you don't go out of the isomorphism class. Okay, you can make birational transformation of the surface, but with the target is a surface which is birational to the original surface, which is isomorphic. Sorry. Okay, semi-rigid means that. Okay, you can explicitly construct somehow the inverse birational map, or another birational map that composed with this gives you an isomorphism. So an auto-birational map of S that then transforms this birational map into an isomorphism. This result was known for D equal 8, but not for D equal 6, and has no sense for D equal 7 and D equal 5. Okay, because there is no non-rational minimal del Pezzo of degree 5 or degree 7.
D between 5 and 8, right?
Yeah. The problem is that I think of points blown up, and so the degree decreases, and oh, I should hurry up. Okay. Mm-hmm. So let me just briefly sketch the classification of minimal del Pezzo. What does it mean to say that the surface is a minimal del Pezzo, and how does this matter in the classification of geometrically rational surface over any field? And so what are actually the interesting cases that turn out to? So as you see, the idea is that you should descend at semi-orthogonal decomposition from some nice semi-orthogonal decomposition on the variety, on the algebraic closure. You can also think about the separable closure if you have problem with non-perfect fields, and try to produce to produce a tilting bundle for which are defined over K to generate categories inside the derived category of the surface. But I just give you a quick classification of geometrically rational surfaces. So geometrically rational means the base change to a rational surface. And we have P2 of K. We have a quadric in P3. Sorry. And we have a minimal del Pezzo. Which means that the Picard group of S is Z and generated by the canonical bundle. So the canonical bundle is always there. There is nothing else than the canonical bundle and the Picard group. So this, you can think of this as a minimal del Pezzo in some other sense, because here the Picard group is generated by hyperplane section. So the canonical bundle has a half canonical bundle exists. And this also, it's minimal del Pezzo in some sense, in the sense that you have a Picard group equal to Z, okay? But it's not generated by the omega. So that's the way I wanna, that's the classical way to consider. And then you have conic bundles over conics. And in this case, the difference is that the Picard group of S is two-dimensional, but it can be minimal. So the theorem of Asher and myself is on these three cases. So these are the cases I want to call del Pezzos. Is in general, a quadric is rational if and only if it has a point. So you can give quadratic forms of rank 4, which don't have point. No. You have rational quadrics with Picard group 1. Yeah. This is interesting because it's exactly the fact that you have, if you have a rational point on your quadric, so you think of your quadric as something like this, and you have the two rulings, okay? But the two rulings are not necessarily defined over the base field. So the two rulings gives rise to these two line bundles. I do it because it's important to understand what happens. And what you want to produce is a tilting bundle for, so you know semi-orthogonal decomposition, where this piece appears in the semi-orthogonal decomposition. So S is a quadric now. And just make another example. So I write down explicitly over S bar, so over the algebraic closure, you have O, O10, O01, and O1. So these hyperplane section descend. So O is defined over any field. The hyperplane section is defined because you suppose that it's a quadric in P. So we are in the case 2. So this is defined over K. The problem is that here you don't. This, you know, Kapranov result, Kuznetsov, they say that actually this category is the category of the Clifford algebra associated to. And you can see the Clifford algebra is the endomorphism algebra of twice this. Okay. So in general, you have something which looks like a degree 2 extension of the discriminant cover of the field K. So it's degree 2 extension, sorry, with the Brouwer class on it, which is the pullback of the Clifford algebra. So the Clifford algebra is exactly the algebra I meant there. Okay. So the pairs of algebra here disappears one of the two algebras because you have a quadric and not an involution variety like here, because you can have something which lives in some Brouwer-Severi class, and this is obstructed by some Brouwer-Severi algebra, and by some Azumaya algebra over K. So you have this degree 2 extension, and the existence of a point implies that A is 0 in the Brouwer group of L, but it doesn't mean that L splits. So it means that you can think as this vector bundle descending to, so end of V is L. If V is defined, end of V is L. But it means that your point here, so this is the point that is in the K point, there is a couple of ruling going through this point, but they are defined only over a degree 2 extension. So you can think of this as a degree 2 cycle. So you blow up the point, you have a degree 2 1 curve that you kill. So you have Picard number 1 because this V is a multiple of this. I mean, it's rank 2. So it, the proof of this. The K0 of the quadric is Z plus Z plus Z. So K0 of LA is just A is generated by A as a simple algebra over L. So indeed, the Grothendieck group of the point you can think of these three cases. They don't have Grothendieck group Z3 because there can be some torsion in weird cases. I mean, what you have is that the Chow group is 3 times Q because you have some degree cycles you cannot rule out, and we don't know what the Grothendieck group is in general. But Grothendieck Riemann-Roch tells you that this is all of these at K0 with Q coefficient equal to Q 3 times. And this is very important for the proof. I just have 10 minutes, so I try to speed up a little bit. So let me just comment a bit the theorem. So the equivalence between having a point of rationality and in the minimal case is and degree. So is a proof by Manin that who shows that Manin shows that. When you have a point, you have a unirational parametrization of your surface, and the degree of this unirational parametrization is 1 if the degree of the surface is at least 5. And then in degree 4, if you have a rational point, it doesn't mean that you have a k-rational surface because you can have you just have a unirational parametrization of degree 2. So I map from P2 onto the surface of degree 2. Okay, and the lower is the degree, the lower is the degree of the surface, the higher is the degree of the unirational parametrization. So you can have points and messy things going on in the Galois group obstructing your rationality for the surface. So the motto, if you want to retain somehow the idea, is that the higher the degree, the easier is the surface, because somehow you can think of the Picard group of S as the G-invariant part of the Picard group of the S over the separable closure. And so you have somehow to make all these exceptional curve descent. So more exceptional curve you have, the bigger is this PKS. So it contains somehow Galois cycles inside. Okay. And there are particular cases where, for example, in degree 7, you can show that there is no. In this case, there cannot happen at the degree 7 because degree 7 is over the algebraic closure is the blue up of the degree 2 point, and if you have the degree 2 point in P2, then in a Brouwer-Severi surface, then it's if you have degree 2 point for a surface, you get a degree 1 point. Somehow you can show that there is no minimal del Pezzo of degree 7, but for example, there are nice examples of del Pezzos of degree 6. Is a very interesting case which are minimal and not rational. And if the degree is 5, last example, there is always a point. So this is a proof by Swinnerton or Dyer, I guess. And you can use the fact that there is always a point to show that it's rational, but it can be minimal, like the surface. You can have del Pezzo 5 with just Picard generated by the canonical bundle, but it's rational. So you have kind of map which you blow up a point and then you contract the degree 5 cycle to get your P2 over K. Okay. And in degree 4. In degree smaller than 4, rationality implies non-minimality. So that's the reason why I can take out minimal from the theorem in the top, because if the degree is smaller than 4, then you know that you have a map to something of a higher degree, and you check what happens in higher degree. Okay, and you use the Orlov formula for blow-ups. So if you blow up something, you just get some kind of these people, like. Okay. Let me just make a quick point on the way we can prove this. Wow. So there is another theorem which is more technical, if you want, which is the following: is if S over K is minimal del Pezzo, so I don't think about conic bundles, okay? Then there exists a semi-orthogonal decomposition of the form given by étale algebras and Brouwer and Azumaya algebras in the Brouwer group of these étale algebras, if and only if Ki are fields. I mean, some of this is cheating because you can, if it's an étale algebra, you can always split into fields. But I want a numerical condition, n is equal to 3. And the degree of S is at least 5. Okay, so somehow the idea is that, so the remark on the Grothendieck group is plugs in exactly here when you want n equal to 3, because if you have such a semi-orthogonal decomposition, you split the Grothendieck group of S into the direct sum of those, and then you just make a calculation. You have to have Q3, so you have to have only 3 elements which are simple, so you want field extensions of the base field, and how do you show that this does not happen in low degree? So that's the tricky point. There is a paper in the 90s was written by Karpov and Nogin, and the idea is that over an algebraically closed field, you can arrange always, if you have a del Pezzo surface or even a quadric. So for P2 and for quadrics was already known by Gorodentsev and Rudakov, and Karpov and Nogin completed the classification for lower degree del Pezzos. You can always rearrange a semi-orthogonal decomposition of the derived category of a del Pezzo surface over an algebraically closed field into 3 blocks, which are made by exceptional bundles with the same rank and the same degree. And when I mean block, it means that an exceptional block is a family generated by vector bundles which are mutually orthogonal. So you have that endomorphism algebra of the block is just a diagonal matrix, and so I'm a bit late. So if S bar is a del Pezzo of degree non-7, because in the degree 7 there's no such decomposition, there exists a semi-orthogonal decomposition into a block E1, E2, and E3 of S bar, where, let me just be very quick, EI are E1, EL, say, I. These are mutually orthogonal, so and when you take, well, I'm lost in notations, so hom between EJ and EK and EL. L is a field, and ES is 0 for every pair of J and S, and for every R here. So it's really a block. So if you take this direct sum of these vector bundles on and these are vector bundles, and if you take E to be the EI to be the tilting bundle, so the sum of these, the endomorphism algebra, of EI is just the matrix algebra. So K bar. Okay, so you can show that such algebra, if they descend to something which is an étale algebra with the Brouwer class. The fact is that if you can produce such a tilting bundle, so you can think of, in the P2 case, the one block is just a line bundle, but in the quadric surface case, one of the blocks is O0, the 2 spinor bundles. Okay, and you cannot descend the 2 spinor bundles. You have to glue them together, And then you can descend them étal locally, and they produce this étal algebra with a Brouwer class on it. And what you can show is that checking explicitly on this. So moreover, Karpov and Nogin showed there is only a finite choice of those. So if you have one of those decomposition, you can mutate into a finite number of those. And then what you can check is that for degree smaller than 5, so 4, 3, 2, 1, what happens is that if you can produce such a tilting bundle on the base, which is étal locally that this E, then there is its Chern class is not a multiple of omega. So the surface cannot be minimal if you can descend this. So if you want to descend this semi-orthogonal decomposition into into three pieces, you will produce a line bundle in the Picard group as the first Chern class of some big vector bundle, which is not the multiple of omega. So the surface will not be rational. And in the other direction, when you have, you can, so the point is that you know that if the surface is minimal, then K0 is Q 3 times with rational coefficients. So you are obliged to have such a decomposition with 3 étal algebras with Brouwer classes on it. And if they base change to things of this form, because the étal algebra base change to the product of field. So if you have an étal algebra, the base change of the étal algebra is just a diagonal matrix. Okay, so if you wanna produce a semi-orthogonal decomposition of this form on a minimal de Pezzo, then it has to base change to a block like this. But if it base change to a block like this, it means that if the degree is less than 4, then you have a vector bundle which gives you a first Chern class in the Picard group, which is not a multiple of omega, so S is non-minimal. And on the other direction, you can construct explicitly for all surfaces of degree bigger or equal than 5 such a semi-orthogonal decomposition, and checking that so the Moritz equivalence of so the zero dimensionality of the semi-orthogonal decomposition gives the rationality, and in this we use results of Blanc, Sierra, and Smith that produced semi-orthogonal decomposition for the Pezzo 6, and some result of Kolyot-Helen, Karpenko, and Merkuriev, which identify from this algebra on Del Pezzo 6 the birational class of the Del Pezzo 6. Okay, I'm being sketchy, but I'm over time. I'm sorry. No, this is Karpov and Nogin. So it's, let me write the name, Gorodentsev, Rudakov, and Karpov and Nogin. So Moscow school in the 90s. So they have this Rudakov seminar on vector bundles, and then they went on studying this fact, and the paper of Karpov and Nogin, which is so these two guys provided this thing for P2 and the quadric. So the problem is not producing such a block. It's showing this all blocks, all the things that you can write in this form, you can mutate them back to some kind of original block, some easier. That's the theory of helices. They call it like this. And so for P1, it's O, O1, O2, and then you can show that any exceptional collection on P1, on P2, sorry, can be mutated to this. And for the quadric is Rudakov, and for other Del Pezzos is Karpov and Nogin. So they do it for C, but the way they do it is just knowing that the Del Pezzo of a given degree is the blow up of projective space, and then playing around with mutations. Blanc, Sierra, Smith, they do it for the Pezzo 6. Yeah, that's what I say. That's what I say. So the other direction. So for degree smaller than bigger than 5, for the Pezzo 6, there is the semi-orthogonal decomposition is given in this way, so, and you can check. We did it with Asher that the semi-orthogonal decomposition described by these three guys, sorry, base changes to the block of the composition of Karpov and Nogin. You can just write down explicitly what happens, and the point, yeah, okay.
So, do you know if these tilting bundles have
I mean, I can just say if they exist, they have some form.